Alrighty, so in this next installment of RScript walkthroughs, I'm going to finish up the week 7 walkthrough looking at t-tests. So for this bit of the tutorials, we're just looking at those t-tests. I've already loaded all the packages that I need to load. I've made sure that my working directory is already set. And when we think about t-tests, okay, remember that we are going to be using t-tests to compare numerical data. So as you've read and as we have gone through in class at this point, there are 3 different types of t-tests. And in this walkthrough, also in the RScript, I am walking you through each line of the code, and we'll go through each of the 3 different types of t-tests. So first up, we have the Onesample Ttest. And to illustrate this Onesample Ttest, we're going to be using example 11.3 from your book. And example 11.3 is looking at normal human body temperatures. And the idea behind this problem is looking at some measurements of human body temperatures taken from randomly chosen healthy individuals. And we want to compare those values to the value of 98.6 degrees Fahrenheit, which is what is always stated as the normal, healthy, not sick body temperature. All right, so if we walk through this here, our null hypothesis is going to be that mean human body temperature is 98.6 degrees Fahrenheit. Our alternative hypothesis, these are two-tailed hypotheses here, and the alternate hypothesis is that mean human body temperature is something different than 98.6. So it could be greater than or could be less than. All right, so as I said, you should recognize that this is a two-tailed test. And you already have these data files. This is exactly what you did in lab before spring break. Okay, so I'm loading in this file, BIO310, week 07 data, temperature. It has headers, so we say header equals true, and I'm calling it temps, simply because that was easy shorthand for what I felt like calling it. All right, so here are my data. Now, granted, there are not a lot of data points here. There's only 25 data points. If this was an actual study, even if this was one of the studies that you might do for your project, for instance, you would want to have many more data points than this. Okay, so here I'm just calling up the column names for this temps data frame that I have. I don't really need to do this because I know that it's called temperature. I can see that it's called temperature right there. It didn't fill up my R console too much that I can't see it. But I like to have this line in my code simply so that I can call this up. I could then simply come in here if I needed to refer to this column, and I could copy that and paste it if I wanted to, ensuring that I wouldn't have any issues with misspellings. All right, so to run this t-test, it's really pretty simple. We just enter t.test. Temps here tells it this is the vector that we want to be looking at. This is the data here. And mu, this is our reference value, 98.6 that we want to compare to. So when we look at our output, we have a Onesample Ttest. It's telling us data is temps. It gives us our test statistic, so our t value of negative 0.56065. It tells us our degrees of freedom, 24, and it also tells us our p-value of 0.5802. You get some additional information here. So the alternative hypothesis here is that the true mean is not equal to 98.6, and you will recognize that is the alternate hypothesis that we talked about up here. And we also get 95% confidence intervals, and it tells us also conveniently our mean. Okay, so sample estimates, remember samples have estimates, populations have parameters, and the mean of x here is 98.524. Okay? So you can store the results of this test also. I'm not going to show you how to do that here, but you've seen multiple times how we have stored results for a test. Here, a p-value of 0.5802 is greater than our specified level of significance, our alpha level of 0.05. So we would not reject the null hypothesis here, and we would conclude that there does not appear to be any difference between 98.6 and the mean of our values. Okay. Now, if we wanted to do a one-tailed test, if we had a one-tailed hypothesis, you could run these tests like this. Okay, so notice here in this line of code, I said alternative equals less. Up here, when I was simply running the two-tailed test, I did not enter anything akin to that up here. Okay, because the default is to do a two-tailed test. But when I specify down here that alternative equals less, I am looking at a one-sample test. So the alternative hypothesis here, which for the t-test, it spells it out nicely, the alternative hypothesis that we're testing is that the true mean is less than 98.6, our specified mu value. Okay. And in this case, for this one-tailed test, we have a p-value of 0.2901, and so also greater than 0.05. So we couldn't reject this null hypothesis either. And if you wanted to do a one-sample or a one-tailed test where you were having the alternative hypothesis that the true mean was greater than 98.6, then you would type that in like this. And also you see this p-value, 0.7099. We also can't reject the null hypothesis based on this p-value. Okay, so that is a nice quick walkthrough of example 11.3, the one-sampled t-test. And the next thing that I'll go through with you is a paired t-test. So this paired t-test that I'm walking you through, this is example 12.2 on page 330 of your textbook. And in this example, we are looking at immunocompetence in male red-winged blackbirds before and after they have been experimentally given additional testosterone. Okay? So if we pull in our data, here I am defining a data frame, blackbird, and I am reading in the data file. This is what the data look like. And as you look at this, you will notice that there are some additional columns in this data frame. Columns that we don't necessarily need, but if you follow through the rest of these lines of code, you will see how I reference the data in the columns. It's not always necessary to pull out a column and define it as a variable to refer to it. We can simply refer to Blackbird and the particular columns that we're interested in. Okay. But first, just because we can and because it's always a good idea to practice our skills, if you look at figure 12.2-1, this is an interesting figure showing the values before and after implant treatments, and we are looking at lines connecting the dots here. I'm going to load in the ggplot2 library just in case that's not loaded in already. And in order to do this, we have to rearrange the data first. Okay, so we're taking a little bit of a tangent right now from the paired t-test so that we can look at an example of how to make a plot of these data look like what we are seeing in the textbook. Okay, so if we call this Blackbird for plot, okay, I'm going to stack Blackbird columns 3 and 4. Okay, so this does exactly what it sounds like it is doing. It is putting column 3 on top of column 4. So if we then define Blackbird for plot column 3 as being 1 through 13 here, and if we look at the column names, we're going to define those as treatment versus individual, and then we can call up our Blackbird for plot right here. Okay, so what I did here, I have the values, okay, stacked on top of each other for log before, which was column 3, or can't select it, which was log before column, and I put that on top of log after column. And then just so that we would see the treatment individuals, I told it to number these 1 through 13 and then 1 through 13 again. Okay, so this 1 here for treatment individual is going to connect this log before value to this log after value. Okay. Now I am calling this line of text up here, and here I want to make another column called treatment sort. Okay. And notice here what I've done, I have added another column that does exactly what this column does. Okay, so I did this in 2 different ways. Okay, the first way that I did this was simply by stacking these columns on top of each other here, and then I got a treatment column. Well, it's named treatment because I told it to name it treatment. And then another way that you could do this was by defining the new column, Blackbird for plot, treat sort. This is why we have this name here. And here we are telling it that we want to look in Blackbird for plot treatment, and that the levels are log before and log after. Okay, so 2 ways of getting the exact same result here. Okay, so now if we plot this here, okay, and I'll just move this plot over top of the RScript for a moment. Now you can see that we have implant treatment, we've got before and after. Okay, so here we're looking at Blackbird for plot. In the AES statement, our X is the treatment. Okay, so we have before and after, and then our Y is the values here. We have some points, so we get those using geom_point. I wanted them to be red, and I tried out a few different sizes, and 2 gave me some dots that looked like a nice size. I want lines between them, so I add this geom_line statement, and when I add that geom_line statement, I want it to group those lines based on individual. So having it like this means that it's going to draw a line between the before for individual 1 to the after for individual 1. Here with the labs, I'm just telling it what I want the x-axis to be called, what I want the y-axis to be called, and then in themes we have the panel background, so we're getting rid of that gray rectangle and making it white. We are altering the axis lines to make them nice and black. We're altering the axis text to be black, because if you don't do this, it was a strange gray color before. And we're also editing the axis title to be bold. Okay, so axis title, implant treatment, and up here, antibody production rate. And then I've specified what my Y limits are, okay, so that I could fit everything in here. When I didn't specify the Y limits, I didn't like the way it was plotting this. Okay. And then for the x-axis, we have a discrete axis, not a continuous axis here, because we've got before and after, not continuous numbers. And I've specified what I want those labels to be. Okay. So that was just a little aside showing you how you would create that plot. All right, so if we now move back to the statistical testing at hand, if we remember what Blackbird looks like here, if you follow along in the textbook, you will see that they run their tests on the log.before and log.after data. This is a paired test looking at before and after. And in the next section, in the week 9 RScript, we talk more about testing the assumptions of these different statistical tests. Okay? For now, just know this log before and log after. This is the log of the column of before data, and then the log of the after column. But to run this paired t-test, we simply type in t.test, and the two things we're looking at are blackbird log.before column and blackbird log.after column. And here, to get the paired test, we have to say paired equals true. If we don't say paired equals true, it's not going to run a paired t-test for us. And we see our results for the paired t-test right here. We have the mean of the differences. We have a 95% confidence interval. The alternative hypothesis is that the difference in means is not equal to 0. Our null is that there is no difference between before and after. So that makes sense. The alternate would be that we don't have a 0 difference. And then we have a t-value. Here, this is your calculated t statistic. There's a degree of freedom of 12, and then a p-value of 0.2277. Right, so if you follow along with the textbook, you will see that these results match the book. The only difference here is that we have a negative t-value. Right, if you were to run the test in the reverse order for the x and y, if you were to switch the order of this and this component, then you would get the same number, but it would be positive rather than negative. Okay. However, really that sign, makes no difference at all. I just wanted to explain to you why we have a negative sign here and the textbook has a positive sign for that. Okay. Just to show you that what I said is true here, if we switch the order of these two components here, we have exactly the same results, only now it is a positive t-value. Okay, so that is how we do a paired t-test in R. And the final t-test that we need to do is a two-sample t-test. So for this example, we are looking at example 12.3 in your textbook, and example 12.3 is on page 335. And here we are looking at a genus of horned lizard. The genus is Phrynosoma. And these lizards are really interesting because they have these spines and they're also able to squirt blood out of their eyes. So they're actually named for these spikes that surround their head. And what the researchers were interested in here was trying to figure out if the length of these spines affords them any protection from being eaten. Okay? So they took advantage of the behavior of one of the main predators for these lizards. This predator, the loggerhead shrike, and you can read more about this in the book, they will find a prey, Phrynosoma, that they're going to eat, and then what they do is they skewer the lizard onto thorns or barbed wire, and then the lizard will die and they can come back later and eat it when they feel like it. So the researchers took advantage of this gruesome behavior, and they were able to go out and find some dead lizards, some killed lizards, and measure their spikes. And then they were also able to measure these spikes in living lizards. Okay, so now that we have that background, we can load in our data here. So lizards is the data that we're reading in here from this horned lizard file. We have headers in here, so we say headers true. If we call up the head for lizards, which is just the first 6 rows, we see that we have data for squamosal horn length and survival. So here, if you were to look at all of the values, you would see that the survive column has 0s and 1s in it, okay, indicating living and killed. All right, so to run a two-sample t-test is actually incredibly easy. We simply say t.test. Lizards, this money sign is a string character. It says look in lizards for something called squamosal horn length. Okay, so it's going to look in lizards for squamosal horn length. And it is going to group those together. What it's going to compare, that's what the squiggle tells it here, is going to compare it to the column in lizards called survive. Okay, so lizards survive here. And a very important component that we need to add in here, this var.equal equals true. Okay, this is going to get us a regular two-sample t-test. If we said that variance was not equal by saying var.equal equals false right here, then we would end up with a Welch's two-sample t-test for unequal variance, which is something that you definitely need to know how to do, but not for this example right here, right now. So our results, we have a two-sample t-test. We see that the data that it is comparing, it is looking at squamosal horn length in lizards by survive in lizards. We have a t-value of negative 4.3467, 183 degrees of freedom, a p-value of 2.289 times 10 to the negative 5. So very significantly different here. The alternative hypothesis is that the true difference in means is not equal to 0. Okay, this is very similar to what our null and alternative for two-sample, or for two-tailed tests rather, always is. Null is always that there's no difference. Alternative is going to be your scientific question of interest, and it's going to be that there is some sort of difference. Again, we get 95% confidence intervals, and then we get estimates for our two groups. So our group 0 mean and our group 1 mean. Remember, we've got 1s and 0s because we coded survival as 1s and 0s. All right, so as I said, when you are doing this, you have to put var.equal equals true. If you don't do that, you're going to get a Welch's two-sample t-test. Okay? And you only want to use that Welch's two-sample t-test if your variances are unequal. Okay? All right, so another peculiarity that you see here is that because survival here is coded as a binary factor, 0s and 1s, this or that, because it's coded as a binary, and because x is a numeric value, and you can see that represented here when we look at the structure of this data frame, lizards. Squamosal horn length is numeric, survival is an integer, okay, and if you looked at all of this, you would see that it was 1s and 0s. So in the case where you have a numeric x and a binary y, you enter this squiggle symbol between them. Okay? If you don't put that squiggle in between them and just use a comma, you'll get wrong values in here. If they're both numeric values, then you would simply separate them with a comma. Okay? So remember, this is meant to be a two-tailed test here. If what we were actually interested in was not a two-tailed test, but instead a one-tailed test, then we would structure our null and our alternate hypothesis in a different way, and then we would have to add this alternative equals less or alternative equals greater argument into our code for the t-test right here. Okay? And just because we already have this example up and running, let me show you how simple it is to get this Welch's two-sample t-test. Okay, it's going to be the exact same as above, but we're going to change that var.equal from true to false. Okay, so var.equal equals false, and this is going to give us a Welch two-sample t-test. Okay, notice that the data it's getting it from is exactly the same as above. The t-value that is calculated is exactly the same as above. What differs though, because remember the Welch's two-sample t-test, does a sort of strange calculation with degrees of freedom. So notice that degrees of freedom is drastically different in this case. And we also end up with a very different p-value here. So remember, the Welchs two-sample test, this is going to be one of those alternative tests to use if you do not have equal variance. So for these data, the correct way that you'd actually want to run this is what you see above with the two-sample t-test here. But I just wanted to show you how easily you could change a single letter in the code here to switch this to a Welchs two-sample t-test. All right, so this concludes things for the walkthroughs of the week 7 RScript.